Yes, yes, yes. Only 8 students are there in the class. Rajesh,
Sir?
only 8 students have joined. Any problem?
No, sir. They are joining, sir.
Okay, okay. Or are they taking this as a weekend? Yeah, it's 9 o'clock. 9 students, 9 o'clock, 10 students. Yeah, we are moving ahead with the second part of Unit 1. Unfortunately, few interruptions are taking place. And the last class, we had an introduction to the general problem solving methodology, what state space is, what control strategy is, and we have looked at a problem, a very familiar problem, that is water jug problem. And in general, what exactly you mean by problem solving is, it's nothing but you are given a task is there with us. We need to give a solution for the task. It could be any kind of task. It doesn't matter. It could be any kind of task. So we'll have a starting state and reach an ending state. So in order to move from a starting state to ending state, what we do is we follow a procedure. We'll have a state space which will have all possible states, and we'll have a set of rules which we normally call it as the production rules. So using the production rules, see, we are not following which production rule is to be followed after what. We are randomly picking up the production rules based on the convenience such that it gives a solution for us. So we are not using any operators, or we are not using any heuristic functions to choose the production rule. So as of now, what is that we are doing is we are randomly picking up the production rule such that it applies to the problem and moves ahead. So based on that, we have solved one. As I said, it's indeed a very familiar problem. Anyone who is dealing with artificial intelligence or who is learning artificial intelligence, definitely they discuss this problem. That is the water jug problem, and I've discussed this in the last class. And what does this problem tell you is you are given two jugs of two different capacities. One is 5 gallon capacity, the other one is 3 gallon capacity, and the objective is to fill the 5 gallon jug with 4 gallons of water, and there are no markers on this. No measuring markers are available on this text. So what the first thing that you need to do is you need to generate the start state and the goal state. So this is how you present your problem. This is your start state and this is your end state. See, we are worried of only of the first jug, where the capacity is 5 gallons, where we need to fill it with 4 gallons of water. And the second jug, you could have any quantity of water, no issue. That's not an issue. And for this, what did we do is we have considered the set of production. And please see my sincere appeal to everyone: do not go with the wrong impression that this is the only set of production rules. These are the production rules for the given problem. You may change this production rules. You can change the order of the production rules. Nothing wrong with this. You can come out with your own set of production rules. But definitely those rules should be applicable to your problem. That's how you need to generate the production rules. And do not go with the wrong impression. Okay, this is a fixed set of production rules, and for every problem that's relevant to water jug, we have to follow these production rules only. Don't go with this wrong impression. Okay, these production rules are to be developed, are to be generated, and we need to apply it to our starting state. and a production rule can be applied any number of times. Okay, our ultimate goal is to reach the goal state, that's the desired state. So this is one kind of say, and there could be several solutions. There could be several solutions. So this is one solution where you started with 0 0 and reached 4 0, because we are not worried of the state of the second jug, we are only worried about the state of the first jug, where 4 gallons of water should be there in the 5 gallon jug. See, I've also given you another solution. You may come out with a different solution also. Don't go with an impression that these are the only possible solutions. Why did we come up with two solutions? Just to tell that there are different possibilities of solutions taking place. See, look at this. At this state, that is at the eighth step, you have 4 gallons of water and 0 gallons of water in this. One, రెండు వచ్చేది. Yes, so this is what we discussed regarding the first problem with respect to the problem solving using the set of production rules. Okay, it's 9:05. Let me see how many students joined. Yes, good number. 39 students joined. Let me continue with the session. Yeah. This is another interesting problem. You might have come across this problem also in your childhood days. Your teachers might have been speaking about this. If you study the problem, see that's visible, that's there on your screen, you'll come to know, oh, this is something that you have come across maybe a few years back when you were studying in school, or you might have come across this in magazines. See, what does the problem tell you is this is a problem relevant to missionaries and cannibals. See, just to make you aware of how to solve problems, we are coming out with certain generic problems. You may apply this technique to any kind of problem. See, what does this problem tell you is 3 missionaries and 3 cannibals want to cross a river. That means they are on one bank of the river, they want to go to the other bank of the river. There is a boat on their side of the river that can be used by either 1 or 2 persons. See, at a time, only 2 persons can travel in that boat. Maximum two. Maximum two. How should they use this boat to cross a river in such a way that the cannibals never outnumber the missionaries on either side of the river? See, the number could be equal. The number of missionaries and the number of cannibals traveling on the boat or on either side of the bank of the rivers, the number of cannibals should never exceed the number of missionaries. If the cannibals, what happens is if the cannibals ever outnumber the missionaries, then the missionaries will be eaten. If there is more number of cannibals, then those missionaries, which is less in number, will be eaten away by the cannibals. So how can they all cross the river? How can they all cross the river without anyone being eaten? That's the condition. No missionary should be eaten by the cannibal. So you might have come across this. Did you come across this problem, general problem? Maybe in some kind of magazine or some well back, way back. This is an old problem. See, this is the pictorial one. All these 3 missionaries and 3 cannibals, along with the boat, they are on one side of the river and they have to move to the other side of the river, satisfying the constraints. Satisfying the constraints. Okay. Can you solve it? And if you want to solve it, how do you do it? You need to generate a set of production rules. You need to define your problem first. See, this is what the problem statement is. Based on that, go with few assumptions, initial assumptions, and then generate the set of production rules, and then apply the production rules such that you reach the desired goal, the desired state. See, this is how the problem is organized. set of ordered pairs of left L, that is left side of the river, that is left bank of the river and right bank of the river. L stands for you are onto the one side of the river. R stands for you are onto the other side of the river. Each bank is represented as, see, each bank, that means based on the number of missionaries, the number of cannibals and the status of the boat, they are represented as a three tuple. They are represented as a three tuple. What does this stands for? This NF, number of missionaries. MC stands for number of cannibals, and B represents the state, the boat. Whether the boat is onto their side of the river or the other side of the river. Okay, this L stands for the left bank of the river, R stands for the right bank of the river, and this is the tuple, three tuple, where the tuple represents the number of missionaries, the number of cannibals, and the representation of boat. So this is how the problem has been stated. The given problem has been represented. Now, so what could be the state space for this? What will be the starting state? On one side of the river, you have three missionaries, three cannibals, and one boat. Now, and on the other side of the river, what's the state? Since all these people are on one side of the river, definitely on the other side of the river, you will have zero missionaries, zero cannibals, and zero boat. Now, the goal, what should be the goal state? From this side of the band, all these people should move to this side of the band such that no missionary is eaten away by any of the cannibals. So the goal state would be, say, if all these people are on to the left side, let's assume so, then the right side is empty. Now the left side should be empty and the right should be full. Now intermediate states. Intermediate state. If you consider any two possible states, let N1M, the number of missionaries, M1 cannibals, and the boat state, N2M and M2. See, suppose if you have this possible state, what do you mean by this possible state? Definitely, this number of missionaries, the number of missionaries should not be less than this number of cannibals. Please understand that. Suppose if the number of missionaries is less than the number of cannibals, what happens? The number of missionaries will be eaten away by the number of cannibals. So the condition should be N1 should be greater than equal to M. And N1 is not equal to 0. This N1 should be greater than or equal to. So you can have equal number of missionaries and cannibals, or you can have more number of missionaries than cannibals, but you should not have less number of missionaries than cannibals, because in the given problem, what does it state is, if the number of missionaries is less than the cannibals, definitely the cannibals will eat away the missionaries. So the condition is written as N1 is greater than or equal to M1. The same applies for this also. N2 greater than or equal to M2. And what is the sum of these two, N1 plus M2? That should be equal to 3, because the problem state there are 3 missionaries. And what will be the sum of M1 plus M2? 3. So this condition is to be satisfied at every state. This condition is to be satisfied at every state. And this boat can be either onto this side of the river or onto this side of the river. So this is the intermediate state. This is the start state, this is the goal state, and this could be any intermediate state. Okay, that's how so you can find the solution. So this YouTube presentation link is there. If you go that, you can listen to the video also. Okay, so these are the production rules for the missionaries and the cannibals problem. If you see, when we say the rule, how does it appear? Just recall your if statement in C language. If it is true, then the action has to take place. Not if else. I'm not speaking about if else. Simple if statement. So on the left side of the rule, we call it as normally antecedent, and the right side of the rule, we normally call it as the consequent. So this is the left side of the rule, and if this is satisfied, when you apply this rule, this is the state that you are going to reach. The right side of the rule is the state, new state that you are going to reach. So these are these first five rules. These first 5 rules are to move the boat from the left side of the bank to the right side of the river. This remaining C, so that's the reason they are labeled as L1, L2, L3, L4, L5. That means from left to right, you're moving. Now this one, R1, R2, R3, R4, R5, to move from right to left. So let's see. I'm not see. You please try understanding all these protection rules. See, look at this. The rule number one. That is which is moving from left to right. N1M, M1C, one boat is there, and the other state N2M, M2C, 0B. So what happens over here? See, this is the intermediate state as presented earlier. This is the intermediate state. So if this rule is being applied, what will be the right side of part of the rule? So based on this, n1 minus 2 m comma, see, it could be any state. Based if n1 is greater than n1 should be greater than or equal to m1. You have to satisfy that condition also. N1 minus 2 m, that means there are two persons moving, two missionaries moving, M1C and 0 boat. This boat has moved to the other side. So N2 plus M, that means two missionaries are moving. Two missionaries are moving. So definitely the number of missionaries will reduce by 2 and the number of missionaries onto the other side will increase by 2. That's how you have to understand. And M2 cannibals, and since the boat has moved from this side to this side, what happens here? You will have 0 boat and here you will have 1 boat. That's how you have to understand the solution and the rules. So look at the first rule again, N1M, M1C, 1B, and N2M, M2C, 0B. If this rule is being applied, then this would be the action that's going to take place. N1 minus 2M, M1C, 0B, N2 plus 2M, M2C, 1B. Look at the R1 rule. That is, you're moving from right side to left side. N1M, M1C, 0B, that is 0 boats. N2M, M2C, 1 boat. See here, onto the left side, the boat is there when it moves. And when you are trying to move it on, the other part, the other side of the river will generally have 0. So here onto the right side, you have the 0 boat. That means the boat is not present onto the right side. What does that imply? On the other bank of the river definitely should have the boat. So when this rule is being applied, what happens? Since, see, onto the right side, you do not have. Onto the left side, you have. So when this rule is being applied, the boat moves to the other bank of the river. So definitely you'll have boat over here and you here, you will not have the boat. Accordingly, if you go with an assumption that two missionaries are moving, then this it will be increased by N1 plus 2 missionaries and this will be decreased by N2 minus 2 missionaries. That's how you have to frame the rules. Please do not by heart these production rules. And you can frame your own set of production rules. Please understand that. Okay? You try understanding, at least trace this. Trace this so that when you better understand this, start framing your own set of rules. See, as I've said, here you have the YouTube video link. Try visiting this YouTube video link. Look at the second rule, N1M, M1C, 1 boat, N2M, M2C. See, look at both the states are similar. But when this rule is being applied, this is the state you may expect. There is only one missionary and one cannibal. So N1 is, so the number of missionaries that will be reduced in this at this particular left side of the state will be N1 and N1 minus 1, and number of cannibals will be reduced by M1 minus 1. Since the boat is present here, when it moves to the other side, the boat becomes 0. Since 1 is moving, then now this will be N2 plus 1, N2 M1 M2 plus 1 and 1 boat. Kindly understand this. In the first case, two missionaries are moving from left side to right side. In the second rule, L2, one missionary and one cannibal is moving to the other side of the river. In the third case, two cannibals are moving. No missionary is moving, two cannibals are moving. That's the reason the number of cannibals is being increased onto the other side. And the fourth side of the rule, one missionary is moving. Only one, because at a time in the boat, either one or two persons can move. It could be cannibals or missionaries. That's not a problem. But either one or two can only travel in the boat. So in the fourth case, what's happening? One missionary is moving and no cannibals are moving. In the fifth case, what is happening? One cannibal is moving and no missionary is moving. So these are the identified possible protection rules. Kindly understand, I'll repeat this. In the first case, if this is the intermediate state, what is happening is two missionaries are moving from left side of the bank to the right side of the bank, right side of the river.
Sir,
In the second rule, yes, Sama?
I have a doubt, sir.
Yeah, please.
At the starting, number of
Yeah,
carnivals and missionaries are equal, right, sir?
yeah.
If we are sending two members to the other side of the bank, then number of missionaries would be less than the carnivals, right? So then they will be
Yeah,
equal.
yeah, yes. See, it is up to you which rule is to be properly used. These are the possible rules we are generating. I'm not applying this rule. When I want to solve this problem, I'll apply a rule where the condition would be satisfied.
Okay,
Are you
sir.
getting it? Are you
Yes,
getting it?
sir.
I'm not applying these rules in this particular sequence
Okay, sir. I
because the
got it.
const
Thank you.
you got it, Amma? Yes, thank you.
Yes, sir. I got it.
Yeah. So in the similar way, the remaining five rules from moving right side of the river to the left side of the river have been given. In the first case, two missionaries are moving from right side of the river to the left side. So two missionaries is being added to the left side and two missionaries is being subtracted from the right side. Similarly, one missionary and one cannibal is moving from right side of the river to the left side of the river. The similar is this is from left to right and this is from right to left. In the third case, two cannibals are moving. Two cannibals are moving. In the fourth case, one missionary is traveling. In the fifth case, one cannibal is traveling. See, as the girl has rightly asked, see, if I apply this rule, what happens? Definitely on one side of the river, the number of cannibals outnumber the number of missionaries. In that case, what happens? The cannibals would eat away the missionaries. So definitely, based on the situation, I have to apply the respective rule. These are only the rules that I've identified, or for the problem we have identified. Now we have to apply these rules. We have to apply these rules. Okay. Now let's see what's happening. What's the initial state as we have already defined? Onto one side, so let's go with an assumption that we are all the missionaries and the cannibals and the boat is onto the left side of the river, and we are trying to move from left side of the river to the right side of the river. Okay. So what is happening here is three missionaries, this is the initial state, three cannibals and one boat. And see, onto the right side of the river, what do you have? You have nothing. Now see, what does it say? In the first step, we are using rule number 2. What does rule number 2 state? Rule number play. See, if you look at this rule, it appears to be a bit confusing. That's the reason I've given you the general description also. See, if the space is available, we can have the general description. What are this state is one missionary and one cannibal is moving from left side of the river to the right side of the river. So, if one cannibal and one missionary is moving onto the right side of the river from the left side, how many missionaries and cannibals would be staying at the left side of the river? So this is the action, see, the right side part. Two missionaries and two cannibals are onto the left side of the river, and one missionary and one cannibal, and the boat also reaches the right side of the river. Are you getting this? So which rule we did apply? The rule 2. Suppose if you have applied rule number 1, that is L1, definitely as the girl has asked me, one of your friends has asked me, definitely the missionary would be in away. Okay, Nama? So this is initially I have applied rule number L2. Rule number L2. See, since I have used rule number L2, do not go with the wrong. Again, I'm telling you, do not go with the impression that, oh, we should go with first this L2 rule only. See, our constraint, we have to satisfy our constraint and apply the respective rule such that we move from the start state to the goal state. See, according to this solution path that has been given over here is the next rule that has been applied is rule number 4, R4. What is does it state? One missionary is moving from right side of the river to the left side of the river. One missionary is moving from right side of the river to the left side of the river. So what will happen? On the right side of the river, you have only one missionary. So definitely when it moves to the left side, now you will have three missionaries, two cannibals, and the boat has come this side. Since this missionary has also moved from right to left, you will have zero missionaries, one cannibal, and zero boats. Can you understand this? Next, which rule has been applied? L3. Yes, one. What does L3 tell you? What does L3 tell you? Two cannibals are moving. Two cannibals are moving from left side of the river to the right side of the river. Two cannibals are moving from the left side of the river to the right side of the river. So definitely what happens? You here you have two cannibals only. Here you have two cannibals left over. So if these two cannibals are moving from this side of the river to this side of the river, definitely what happens? You will have zero cannibals here and three missionaries. And onto the right side of the river, you will have three cannibals. No missionaries. That's the current state. Now, which rule is being applied? Rule number R5. And what does rule number R5 tell you? Something is moving from right side of the river to the left side of the river. What is that something? What is that something? One cannibal is moving from right side of the river to the left side of the river. So what happens? You will have two cannibals over here. You will have 3M and 1C over here. Three missionaries and one cannibal, and the boat is now. Now rule number 1 is being applied. Now rule number 1. What is rule number 1? Kindly make a note. Two missionaries are moving. Two missionaries are moving from the left side of the bank to the right side of the bank. So what happens now? Since two missionaries are moving, one missionary is left over here. One missionary is left over here. One missionary is left over here. And the cannibal is not moving, so you will have the same number of cannibals. And since two missionaries are moving over here, you will have two missionaries and two cannibals. See, at no point our constraint is being violated. Our condition is being violated. If the condition is violated, what happens immediately? The missionaries would be eaten away. And next, rule number R2 is being applied. What does R2 tell you? What does R2 tell you? One missionary and one cannibal is moving from right side to left side. So here you have two missionaries, two cannibals. Now this would be added to this. Two missionaries and two cannibals. This is balanced, so no problem takes place. So you'll have two missionaries and two cannibals on the left side and one missionary and one cannibal onto the right side. Now again, rule number L1 is being applied. What does rule number L1 tell you? Rule number L1 tells you move two missionaries from the left side to right side. So now you will have three missionaries and one cannibal over here. Two missionaries and one cannibal over here. Now what is rule number R5 is being applied. Rule number R5 is being applied. And what does this rule number R5 tells you is move the cannibal from the right side of the river to the left side of the river. So you will have three cannibals over here. Three cannibals over here and three missionaries over here. Next, rule number L3 is being applied. What does L3 tell you? L3 tells you move two cannibals from left to right. Move two cannibals from left to right. So if you apply this, one cannibal is left over here and two cannibals go over here. Two cannibals go over here. Next, R5 is being applied. R5 means from right side to left side. That is, one cannibal is moving from right to left. So you'll have two cannibals over here, one boat. And then finally, L3 is being applied. That is, two cannibals are moving. Two cannibals are moving. So then finally you're left with zero missionaries, zero cannibals, and zero boat. And all the three missionaries, three cannibals, and one boat have reached the goal state. See, based on the production rules I have developed, this is the solution I have come across. So if you change the rules, if you change these production rules, you'll have a different solution. And if you go with the way which production rule is being applied, you may have a different solution, as we have seen in the water jet problem. You see here, these rules have been developed with the assumption that All the three missionaries, three cannibals, and the boat is onto the left side of the river. So we are planning to move from left side of the river to the right side of the river. Suppose if you go with an assumption that all the three missionaries, three cannibals, the boat is onto the right side of the river, then you try applying the R rules first. So accordingly, you have to move. So this is the solution path for the given problem. So what is interesting over here is, what is that you have to make a note over here is, you have to initially define the state of the problem. See, this is the description of the problem that has been given. From this description of the problem, you have to mathematically represent them. You have to mathematically represent them. See, how did we identify left by L, right by R? And then how did we make this tuple based on the number of missionaries, number of cannibals, and the number of the boats, which specify the state of the left side of the river or the right side of the river. Left side of the river or the right side of the river. And then we have given the state space. What does it tell you? What is the starting position? What's the ending position? What is the intermediate position? What's the intermediate position? Based on this, we have generated a set of rules from moving from left to right and the vice versa, that is moving from right to left. You'll have the same set of rules, see, only the direction is changing. Only the direction is changing, that is left to right and then right to left. All of that. See, the first rule, clearly understand this. Don't go with this notation. This might confuse you. The first rule is moving two missionaries from the left side to right side. Accordingly, give the state. The second rule is moving one missionary and one cannibal from left side to right side. Then the third rule is moving two cannibals from left side to right side. That's how you have to understand. And the fourth rule is moving one missionary from left side to right side. And the fifth rule is moving one cannibal from left side to right side. The same description for moving from right to left. Two missionaries are moving from right to left. Next, one missionary and one cannibal is moving from right to left. Next, two cannibals are moving from right to left. Then one missionary is moving from right to left. And finally, one cannibal is moving from right to left. That's how you have to understand the descriptions of these rules and then apply the rules to the given problem. You will have this set of rules being applied in this particular sequence so as to reach the desired state. Okay, Namu, is that clear? So this is how.
Yes, sir.
Any queries? Any queries? This is how you have to apply the production rules to any given generic problem. See, in C language might be R19 regulations. Now, in C language, you have problem solving with C. See, the questions were not given directly to you. You were given problem statements and you are asked to provide solutions. And that knowledge would be useful for you over here. Okay? You have to understand the problem, make out the statements, generate these production rules, and then apply to obtain the solution. Yes. This is, and see, we have stated something like state space. What does state space tell you? State space is going to provide you all possible states of the problem. And all possible states might not be used in obtaining the solution, but you need to generate all possible states. Suppose if I ask you, when you are playing chess, and most of you are good at playing chess, I think. What are the possible states if I ask you? What could be the possible states? There could be good number of possible states. It depends, it varies from person to person. So when I play, I may play in a different way. And when you play, you may play in a different way. You may choose a different coin and then accordingly move. So I need to represent all possible states, keeping in mind that different types of players will be playing the game. So that large space of possibilities is nothing but called as the state space. And what does this slide tell you is, how do you set the state space search? In the previous case, we are not following any methodology to search the state space. We are randomly picking up the production rules. We are randomly picking up the production rules. Now, this we need to go with some kind of confinement, some kind of notation for applying the rules. The state space is another method of problem representation that facilitates easy search, such that it applies a rule. Or see, when you want to apply a rule, let the rule be chosen in such a way, rather than randomly choosing, let it be chosen in such a way satisfying some kind of parameter. That's what state space search tells you. Okay, using this method, one can also find a path from start state to goal state while solving a problem. Definitely, yes. We are going to use the state spaces to solve the problems only, but we are going to apply the state space search systematically. So a state space is basically consists of four components. These are the four components. Kindly make a note of this. These are the four components. A set S containing the start state. So this is the initial state, the beginning state. A set G containing the goal state. That is the final state, your desired state. So the first two are very clear. The first two are very clear. And whenever we say state space set, you will normally be representing it in the graph format or the tree format. And mostly it is acyclic. Okay. Set of nodes, that is intermediate in the graph. See, all the intermediate states will be represented as nodes in the graph or tree. Graph or tree, you either go with the graph notation or go with the tree notation. All the intermediate states will be represented as nodes either in the graph or the tree. So each node represents the state in the problem solving. That's what I mean. State means the intermediate state. Set of arcs connecting nodes. So definitely when you move from one state to another state, you need to connect it by an edge. That edge is nothing but the arc. And what does this arc represent? That you are applying an operator, you are applying a rule. You are applying a rule, you are applying an operator, or you are applying something. Each arc corresponds to operator. That is a step in a problem solving process. A step in a, that is, you are trying to apply, see, left side of the rule is to be applied. That's what the operator is. If the left side of the rule is applied, what does it imply? The right side is nothing but the action to take place. So these are the four steps. The initial state, yes, the goal state G, the intermediate states represent the nodes in the tree or graph, and the arcs connecting the nodes represent the action being taken, which rule is being applied and what's the following action. That's what you mean by these four possible four components of the state space search. Next, a solution path is a path from, see, what is the clearly said in the third line? The nodes are represented either in the graph or state. So you always start from this. So that is the root node, where the root node will have the starting state, and you will follow a path from the root node to some kind of leaf node, which would give you a solution, that is node G. So a solution path is a path from the graph from a node S to a node G. And what's the objective of this algorithm? To determine a solution path in the graph or tree. And as I said, see, as we said, there could be more than one solution for a given problem. Suppose if I ask you to find out whether the number is prime number or not, is there only one solution for that? There are different types of solutions. You can use Fermat's theorem to check whether the number is prime or not, or the simple solution, find the number of factors and check whether it is equal to 2 or not, or you can run up to square root of that. So there are different ways of representing it. So there could be several solutions for solving a problem. One solution path is selected based on some criteria of goodness. See, even though there are several solutions, normally you go with an optimal solution. And that optimal solution is normally chosen using the goodness function or the heuristic function. That means when you choose the rule that's being applied, we'll apply this goodness function or the heuristic function such that we obtain a optimal solution. Okay. Earlier in the previous cases, what did we do? We have not followed anything. We have randomly chosen a rule based on the application. Commonly used approach is to apply appropriate operator to transfer one state from of problem to another. That is to move from one state of the problem to another problem, we'll be applying the rule. That the operator we call it as or the rule, the left side of the rule. See, this is again the problem relevant, the previous solved problem only. Consider again the problem of missionaries and cannibals. Possible operators are two missionaries, zero cannibals. See, these are the possible states. Because what's the condition? The cannibals should not outnumber the missionaries. Two missionaries, zero cannibals. One missionary, one cannibal. Zero missionaries, two cannibals. One missionary, zero cannibal. Zero missionary, one cannibal. These could be the possible states, possible operators, the next states. So M stands for missionary and C stands for cannibal. See, if one of this is the possible state, nothing happens. Everything runs smoothly. If the boat is on the left bank, we use the operator. This is a right arrow. And if the boat is on the right bank, we use the left arrow. The state is represented as L to R. See, these are the notations before solving the problem. L is to R. What does L represent? The state of the bank at the left side of the river. N1M, M1C, and 1B. What does the right side of the river? Since you are assuming that the boat is on the left side of the river, definitely there will be no boat on the right side of the river. N2M, M2C, and 0B. See, these are the possible states. And these possible statements, these are the possible operators. And what is the starting state? Three missionaries, three cannibals, and one boat. Onto the left side, colon. Onto the right side, what do you have? Zero missionaries, zero cannibals, zero boats. Or you can simply write it as 331 colon 000. See, before this colon, you will have the left side of the state. After the colon, you will have the right side of the state. When you reach the goal state, what should be this? This should become 0 and this should become 3M, 3C, and 1B. This is how we are defining the problem. Now let's see. See, when you are trying to apply these rules of the operators, we need to filter invalid states. Certain states are invalid because what exactly do you mean by invalid state? One missionary and two cannibals. Definitely the missionary would be eaten away. The missionary would be eaten away. Such kind of states should be taken into consideration because that's violating the rule. That's why it is required of the problem. So that's what it is. We need to filter invalid state, illegal operators, not applicable to some states and some states that are not required at all. For example, this is an invalid state. So, and in case of valid state, is this valid? Two missionaries, two cannibals. Is it valid state? Two missionaries, one cannibal, or zero missionaries, two cannibals. See, this is not required. Zero missionaries, one cannibal, zero missionaries, two cannibals. See, even though this is an valid operator, that's illegal, not necessary. Okay, applying the same operator both ways would be waste of time. This is applying the same operator both ways. What happens? It gets in a looping state. It gets in a looping state. You start from one state, move from the left side of the bank to the right side of the bank, and again apply a reverse operator, which will give you the initial state again. So that's normally we call it as looping situation. Since we return to a previous state, it is called as a looping situation. And looping may occur after few steps. Such operation should be avoided. See, these are the things that you need to take into consideration when you apply the problem. Unnecessary things should not take place. Invalid state should not be taken into consideration. Illegal operator should not be applied. And you should be careful while using the looping statements. Okay? And see, I don't know whether it is visible to you all or not. This is how the graph or tree appears. I've enlarged it. Let me, yeah. Hope it gives a better view now. Yeah. Is it now visible? Yeah. So you look at the root of the state space tree. The initial state is 331, that is on the left side of the bank, you have three missionaries, three cannibals. We are going with simple notation. And on to the right side. Now, which particular operator is being used? Which particular operator? So, in the previous slide, we have seen the operators, all the legal operators only we have considered. One missionary, one cannibal. Suppose if this operator is applied. See, this R normally represents what? The operator left side of the rule that's being applied. That's the operator that's being applied. And what will be the new state? Two missionaries, two cannibals, and zero boat will be on to the left side, and one missionary, one cannibal, and one boat will be on the right side. Suppose this operator is applied, zero missionaries, two cannibals. Then what happens? You will have all three missionaries onto the left side, and one cannibal is left over, and two cannibals will be moved onto the right side. Next, another possible operator. Zero missionaries and one cannibal. Then you will have 3 2 left onto the left side and 0 1 moving onto the right side. This is what we mean by the state space set. See, we need to apply the rules. We need to apply the rules, and accordingly, we need to find out all legal possibilities. All legal possibilities. If you see, if you run through this, see, look at this. After this first level, we are at this particular state. Suppose if this rule is applied, now what happens? 3 2 1. That means what is this rule? One missionary moving. See, here it is left arrow. Left arrow means you are moving from right to left. Right arrow means you are moving from left to right. So what is happening over here? This missionary is moving. This one you have one is a missionary to the right side, and that's moving from this position to this position. So now you have 3 2 1. And look at this. Here you have 3 1 0. If we apply this one cannibal moving from this side to this side, then what happens? Then also you will have 3 2 1. See, look at these two states. You obtain the same state. Here you apply two different operators. You have two different states. But here when you are applying the rule, one missionary moving from this side to this side, that's left side to left side. Here one cannibal is moving from right side to left side, and you are ending with the same state. You are ending with the same state. Here, what is that you are applying? Here you have applied 0 1C. Now that is from left to right. Now if you are applying 0 and 1C from right to left, then what happens? You reach the initial state. This is what looping is. See, this part is looping. See, beware of looping. See, by applying a rule that gives you a definite solution. Here you are ending with same solution. So you can explore this part or you can explore this part. You can explore the respective part. Apply the operator, move to the next state. Apply the operator, move to the next state until you reach the goal state. You see, if you keep on moving, see, this is what it tells you, sorry. This is the goal state, final goal state, 0 0 0 3 3 1. See, here you have followed this to two different solutions. So that is two different paths have given you same solution. You started with the initial state and moved to the goal state. At the intermediate level, you have got two different solutions. Maybe at this particular path, this is one solution and this is another solution. The reason we say that there will be several solutions for the same problem. So there were several solutions means several solution paths. Several solution paths. This is what the possibility of applying the state space search space. We are applying, see, this is the initial state, this is the goal state. At every state, when you are moving, we'll check whether we have reached the goal state or not. If the goal state is not reached, then we'll start applying the next operator or the previous operator only. The respective operator will be applied and we'll be moving to the next state. Keep on moving by applying the operators. The operators will be represented on the arrows, that is the arcs or the edges. See, all these are intermediate states. All these are intermediate state. The root is the goal state, and this leaf is the the root is the initial state, start state, and this leaf is the goal state. And there is a possibility of having more than one solution. Do remember that. See, this is what state space search is. See, this is two different solution paths. What do you mean by this arrow marks moving from left to right? This arrow marks moving from right to left. This is one solution path. This is one solution path based on this only. This has been written way this way, and this is represented in the graph format or the tree format. We'll look at this problem in the next class. In the meantime, you two try finding a solution for this. See, this is the initial state of the grid. This is puzzle problems. You might have purchased this way back at the childhood in this jatras, where we try to organize them in a sequence. So this is the initial state, this is the goal state. You fix the initial state, you fix the goal state, and find a solution for that. Try doing this. If you cannot try it out, I'll explain this in the following class. Okay, Nama? Any doubts? Any doubts? Oh, then, okay, Amma CR, thank you. Thank you, Meghna. But somehow I'm not getting the complete strength. Around 10 plus students are being absent on a regular basis. Please do not, if you miss the foundations, the introductory classes, and this problem solving is very important. See, the first part of unit 1 you can by heart if you want, but the second part of unit 1 you need to understand. Then only you can try coming out with your own solution, or you can try writing down your own program. Okay? Thank you all. If no queries, you may leave. Thank you. I'll stop presenting it, and you can leave session. Yes, please stay back and ask me, or else you may please leave the session and join the following class. Hope you have the Haripriyanka madam's class. I'll stop recording.